Okay. Ordinary differential equations, also called ODEs, will form the subject of today's discussion. It is my plan to discuss the kinds of questions one will expect to meet as they open any assessment for this module. First things first, is very important that one understands how to solve systems involving a set of differential equations and transforming them into what we call the triangular systems. I know it's a very easy concept, but obviously it is very examinable, and there's no doubt that you're one who's going to meet a system of differential equations to be solved. And now this system is equivalent to both the following triangular systems. Given the three systems above, separately state with complete justifications your strategy in solving them completely. Okay. We are getting started. Okay, we are most certainly getting started. And let's see what we can do. Right, so obviously now this system here, right, here we go. Right, we note that the system actually can be written in operator notation. And if the system can be written in operator notation, we can label the equations. Normally, this is how the solution is written. Okay, the solution obviously goes as follows. So we label the first equation, and the first equation is the d minus 2. Okay, this is a very interesting notation we use here, the d notation, the d operator. Right, so we have d minus 2, obviously acting on x as an operator. Okay, somebody once argued that this obviously acts as a number. Right, and then you have twice d operating on y. And these operators themselves, this differential equation is this. Okay, what are we discussing here? Okay, it's not about the question, but we're just discussing triangular systems. Right, and the next thing is now we just copy the bottom one. Then we just learn how to transform these into a triangular system. The kind of question we are discussing, the problem does not quite matter. Okay, so we have 3D here minus 1, and it is actually operating on y, and this result is 0. We then normally label our equations on the left-hand side. So that is equation 1, and this one here is equation 2. Right, so these become simultaneous equations, and I'm going to reveal them on the next page. Right, so if I reveal them, therefore, on the next page, we obtain the following. Okay, our objective, first things first, will be to obtain this particular representation as a triangular system. Okay, I'm going to move to the next page or next slide and say, we remember from what I've written, okay, we have d minus 2. I'm just writing them here for us to manipulate this particular system of differential equations. We have this, so then we have twice d y, and this is twice minus 4e to the twice t, and then we have twice d minus 3, and then we have x plus 3d minus 1 into y, which equals 0. Once again, we remember that this is equation 1 and that remains equation 2, and we have that. Okay, this becomes multipliers equations, and therefore we state a particular set of rules. So, yeah, normally you can draw lines, or you might just write in words and say, what is the objective at this point? Is to actually eliminate a given variable, so we can actually try to eliminate or multiply a given equation by 2. Okay, so if we multiply the second equation by 2, so if you say equation 2 times 2, or 2 times equation 2, right, what that gives us, for instance, would be 4d minus 6. Okay, it's just elimination this, okay, and then obviously multiply that, it becomes 6d minus 2. Okay, we're just discussing the triangular systems. As said already, this is a very, very popular school method of solving linear systems, what we call simultaneous equations in school. All right, we get that this one here. And so if you look at these very carefully, we have these particular equations. These particular 3 equations, so we can call this one equation 3, if you like. Equation 3. Okay. And so if we take equation 1 and we multiply it by 3 to eliminate y, because looking at this here, the d operator acting on y has been totally removed. So yeah, that's what we're trying to remove. We multiplied this one by 2, and therefore obviously just want to make these the same. So multiply by 2, multiply the top one by 3. So we're gonna say equation 4. Obviously, equation 4 is the same as equation 1 multiplied by what? Multiplied by 3. Giving us 3d, multiplying that one there, minus 6. X multiplying by 3 becomes 6d y. Multiplying by 3 becomes 6 minus 12 e to the twice t. Okay, if need to be, one can even draw lines to make things a little easier and a bit more organized. Right, at this point, we realize therefore that we want to eliminate y from this. So if we want to eliminate y from this, we can perform subtraction of the 2 equations. So we can then say, doesn't really matter what you do. For instance, we can then say the equation we got, we subtract from the first one. So we can say equation 3 minus 4, or the other way around. You can say 4 minus 3. Right, doesn't really matter. Okay, let me just say 4 minus 3. Well, you can say 3 minus 1, doesn't matter. Right, let me say 4 minus 3. You subtract the second one from the first one. So you subtract this one from that one. So you can say, yeah, doesn't matter quite. Anyway, okay, the result is going to be the same. You can just simplify and divide through by -1, etc. If that is going to be different from what was given on the other side. Right, so if you're going to say 4 minus 3, let's check what we actually get at this point. You can write at the bottom here to create some order. So, for example, what does these give us? Okay, so we have exactly this and we have that. Right. Right, which one is neater? Allow me to say 3 minus 4. So that, okay, I'm justifying that so that now because it's easier to say 4d minus 3d, and then you get a d, right? So if you then say 3 minus 4, it makes the whole thing neat. If you say 3 minus 4. Okay, once again, yeah, but that is neat. You'll forgive me. 3 minus 4. Because if I say 3 minus 4, then it's going to be exactly 4d minus 3d. Okay, so that's going to be exactly d, which is neater. And then obviously if you have the 6 minus into plus 3 there, so that's going to be a big 0. Okay, so that's going to be x like this. Okay, so we continue. Right, so next we actually look at the eliminations methods here. Right, we get this here. And then now we look at the y's. Okay, we have already said 3 minus 4, it's neater. So if you look at the 6d minus 6d is going to be 0. Okay, interesting thing here. So we have this one here minus nothing. That is a constant being subtracted from d. So and that gives us actually minus twice y. Okay, and therefore now we have 0 minus 6, which is exactly minus 6. Okay, 0 minus into minus 12, which is 12e to the twice t. Okay, so we get this. Okay, awesome. Right, so we have the following thing. When we get to this point, we have this particular equation. And this particular equation, we can give it a name, a label, call it equation 5. Okay, we got equation 5. We're just discussing triangular systems once again. And now, at this point, we can easily be in a position to make y the subject of the equation in whatever form. Okay, the easiest way to make y the subject of the equation to transpose the y to the right, making it positive, and then now you have the d operator on x. This one is brought to making it plus, the 12 becoming negative, twice t. Okay. At this point, we can divide through by 2 and getting dx plus 3, dividing that 6 divided by 2. And then you divide the 12 by 2, you're giving us a 6. And this is e to the twice t. Okay. Right, so that's what we are able to obtain, and this is what we get. This is exactly what we are able to get at this point. Right, so we perform further substitution. Right, performing further substitution. So now, if you substitute this particular equation, you can give it a name. Okay, substituting, you can use that. Substituting the last equation into the first equation, we obtain, okay, just a roadmap. Take this one, which is y equals half d. I'm just putting them next adjacent each other here. Plus 3 minus 6. Okay, we're just looking at the roadmap on triangular systems. And where is the first one? The first equation obviously is exactly this one there, and we're going to write it there, obviously. Okay, right. If we write it here, it is exactly d minus 2 x plus twice dy, which is 2 minus 4e to the twice t. Okay, so this is equation 1. So what we do is we perform substitution into this one. And if we do that, we obtain d minus 2 operating on x. Okay, this is a funny operator because I was discussing this and one professor suggested that obviously it is not a good operator. This one, it actually sometimes it acts as a number instead of being an operator. So the professor's argument was, what's the point of this method actually? It's very, very ineffective. Okay, but now you have the dx plus, then you have plus 3 minus 6e to the twice t. Obviously, we're mingling the operator with numbers. It's d minus 2, but the understanding is obvious that if this is written that d is an operator, so we need to separate entities of the same kind in mathematics. So the 2 obviously is not just 2, but it is 2 times the identity operator. Okay, so it has to be taken in that context. So yeah, we're substituting the y, this whole y expression into this slot. We close like this, and after having closed, it is actually therefore equals 2 minus 4e to the twice t. Okay, we're good. And we get this equation. We can call it equation 6, doesn't quite matter. Right, so we then say, call this equation 6. Call this equation 6. Now we then say from 5. Yes, from 5. From 5 and 6. Okay, let's see how the triangular system is going to be written out of that. Obviously, we have achieved. So from 5 and 6, right, we have actually the triangular system. Right, what is the triangular system in the required format? What is the triangular system in the required format? It is the top one that we just got. It is actually the d minus 6, yeah. D minus 2, you close like this. Okay, just all these here, we're copying it. We multiply through by the d8-like terms to be smarter, because we still can perform further algebraic manipulations on the differential equation 6. Right, so we have 3 minus that twice t, and this is this. Okay, this one is the equation 6, and we have equation 5. Right, obviously in comparison with what was supposed to get us the objective, the triangular system in which the y, the d operating on y has been totally eliminated, and we have now equation 5, which is actually the d operator on x minus twice y, which is minus 6 plus 12 e to the twice t. Okay, this is exactly what we have. And then I'm going to say hence. These simplifies to this system. Simplifies to. Okay, so obviously that system sort of simplifies to something. Let's check. Okay, we're going to simplify it pretty fast. Now, this is how we simplify it. If you multiply the highest degree, d times d, it's d squared. But it's 2d times that. So half cancels, giving us d squared. Okay, so we have the d squared. Then we have also, now, yeah, that's the d squared there. Then here you'd have what? Then you would have the d as well. So that's going to be like 6d. And there's going to be a d here. And so we can just write, in the meantime, these together with that. So that becomes like a d. Okay, this one is going to be 0. D on 3 is going to be 0. So, but yeah, but this one is going to survive. This is going to survive, d on x. And then now there is minus 2. This minus 2, and you have the operate on x. Okay, this is too congested, I agree. And then now the right-hand side is exactly what? Okay, now the right-hand side is going to be obtained from some of the things here. Like D on 3 is going to be 0 because 3 is a constant. And then now you have D on the minus 6e to the 2t. So the 2 is going to come down, which is minus 12. Okay, if you have actually a minus 12 and it's multiplied by 2, which is a minus 24, if it goes to the other side, it becomes a 24 minus 4, which is a 20. But it finds a 2 there. So it therefore becomes 20e, the twice t. Then at the bottom, you have the d operator on x minus twice y, which is exactly this equation, is actually equal to minus 6 12e to the twice t. All right. This is too obvious, but we just need to just mention what we did to obtain this result. What we did was to most certainly just eliminate the operator on y, because we had the d operator on y and we totally eliminated that. And after we eliminated that, we had only the d operator on x left. And in particular, if you look at this, d operator on x minus 2y equals minus 6 12e to the twice t. It's exactly this, okay? With the exception of the fact that we have the minus 6 plus the 12, and here they have the 12 minus that. And they have the d squared plus d minus 2 plus 20t. It's exactly this. So the next thing is, okay, the next objective is to try and eliminate the next variable. So we remove the d operator on x, and then we're left with d operator on y. So that's going to give us another triangular system. Obviously, now, given the three systems above, according to this, given the three systems above, state with complete justifications your strategy in solving them. Okay, obviously, strategy has been outlined in terms of the operations that were followed. I know that it is just a warm-up exercise, this one, but we're gonna just in the least amount of steps. We're going to write this equation on the next slide and just to remove. I know that this is one of the easiest modules you can come across. Okay, so I'm going to write down the equation, the given system. Right, so it has equation 1 and it has equation 2, and it is as follows. It is d minus 2. Okay, well, just eliminating y now, and with 2dy, which is 2 minus 4e to the twice t, which is twice d minus 3, like this. And then now, which is the operator on y. Okay. The next thing is now we need to remove x and be left with y, the operator on y. Right. Obviously, these become sort of the regular equations, and therefore, what do we do at these points? Right, so we can easily do that. Okay, I can change the strategy and just draw some lines here like this, and then say, okay, we want to eliminate x, dx, and be able to live. So at this point now, there is a d here, so we can just multiply this one by a straight 2. So we're going to say the number 2 times equation 1. Right, so if we do that, it's going to be exactly twice d minus 4 operator on x, and then we multiply, it becomes 4dy which it becomes exactly 4e 8e to the twice that. Right, so at this point, I want to eliminate this one. So clearly we can see that we can just write the 2 out. Okay, I like just writing these out so that we can have our pair of differential equations, and then we can be able to perform the elimination, because this is just the elimination method, eliminating one variable and obviously leaving the next variable. Okay, we have this, and sometimes have this here. And then now, this one here, we have, so we can say these particular equations in any order. You can say this bottom one minus the top one. So, or the top one, yeah, it's needed to say the top one minus the bottom, because now you're going to have the 4d minus 3d, which is going to give it d. Otherwise, you're going to have a negative d. Okay, it doesn't matter. So we can say 2 times 1 minus,
Hello?
yes, please. So yeah, this is 1. Yes, 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 Aman. So this is too obvious,
Why do
right?
you multiply? Why do you why do you multiply everything by 2?
Okay, that's a good question. Why do I multiply everything by 2? I'm multiplying everything by 2 because we want to remove this operator here. We want to remove the operator on x. So we could multiply by -2 still, but I just decided to multiply this one by 2 so that it could have 2d and 2d, and the 2d's can cancel out. You know, that became the objective. So I decided to multiply, therefore, this one by 2, giving 2d minus 4d plus 4dy plus 4 minus 8, etc. Obviously, the next, what is the objective? The objective is to remove the d operator on x. And we are in that direction sort of making progress. Because if you then take this equation right now, and then you take this one minus this one, we'll then have 2d minus 2d, 0. And then now you have minus 4 plus 3, which is minus x. Right, so like we saw here, when we just had the y left, so we're going to have exactly the same thing. So this is just going to be a minus x, okay? Because these two cancel out. You say this minus that, and then you're left with this one minus 4 plus that, which is minus x. And then now you have this one here, which is 4d minus 3d. Okay, so that becomes a plus d. And then obviously now it's this one minus that, which is going to make this one a plus 1. D operator on y. And then we have this one, everything here minus 0, which is just all that. Okay. Let's see now how far we have come. We have come exactly to this point here. At this point, you can decide to call this a differential equation. So multiplying, and write that one down. Multiplying both sides by -1 for argument's sake. Here, we get x minus, okay, d plus 1. D operator on y, which is 8 e to the twice t plus 4. Okay, now we have got that one, and this one is sort of an achievement for us. Let me just put it in sort of a block here. Put it in a block, in a red block like this. Okay, we got one achievement. And then now, after we got this achievement, we are very close. Why? Because there's this equation that we're supposed to get. X minus d plus 1, 8 minus that. Okay, all
Hello.
right. The 4 is negative because you multiply by -1. So the 8 is positive and the 4 is negative, right? That's what you need to say. Okay, any comments? Maybe there's something else you're observing?
Yes, I was gonna make that comment. It should have been minus.
Okay, thank you so much. Okay, right. Obviously, I'm making reference as well to where we're supposed to get to. So yeah, it's exactly this one. That's why I sort of multiplied through by negative. So you have the x minus d plus 1, 8e to the 2t minus 4. So it's exactly this one. And then now we have to achieve another equation. We have already achieved the equation in particular. So the other equation we need to actually obtain is the equation that is a substitution equation. We've learned this. We've learned this from the initial operation. So this one is obtained by performing a substitution into one of the differential equations. We can substitute into any of them, preferably in the very first one, like we did before. So we can give this one a name and call it 3. And then we'll proceed to say substitute. Right, so we'll say substitute 3 into, okay, it's not nice to substitute yet, perhaps. Okay, let me just perform a little bit of algebra on it. Make x a subject straight away. Right, so let's just do that. If you make x a subject straight away, you get x equals d plus 1, operator on y, and then now, obviously, it is 8e to the twice t minus 4. Okay, yeah. And then at this point, we can give it, let's give it the name equation 3. It's better we label this one because, yeah, this one is okay, but this one x is already the subject. And then at this point, we proceed to say substitute. Substitute 3 into 1. Okay, there it is. And then if we do exactly that one, we're going to have the following. Okay, we're going to have the following. So wherever there is x, we put that. So that's going to be d minus 2. Wherever there is x, what do we put? We put this giant equation, d plus 1. And then y plus 8e to the 2t minus 4. Okay, yeah. Plus twice d operator on y. And this whole thing is actually equal to 2 minus 4 e to the twice t. Okay. Okay, now we have got the triangular system already, but let's just, the practice is to add like terms and multiply out, distribute, etc. So let's perform some basic distribution. Okay, to distribute here, obviously we use the distributive law. We take this, okay, a couple of ways. You can sort of allow d to operate on this and then minus 2 to operate on this. Or we let these operate, okay? Sort of d can be allowed to operate on d plus 1, doesn't matter. Y here, and then plus 8e to the twice t minus 4, okay? It's this now on d minus 2 on this as well, which is d plus 1, and then y, okay, like this, and then plus 8e to the twice t minus 4. Okay, and then now you have the plus twice d on y, which equals 2 minus 4e to the twice t. Right. We are back now, right now. Okay, now we actually allow this. So this is going to be like d, which is like d squared. And it's the highest. There's no other d squared that's going to come up here. So this is the only d squared. Let's just write it down like that. And then after we've got the d squared, let's look at the d's now. this and the 1 is going to be like a D, obviously on Y. So it's going to have a D here. And then now there's going to be a minus 2D on Y here. And then this one now it's going to be a 2D on Y minus 2D on Y, a 2D on Y. So it's going to be 0. We're just going to be left with the D on Y. So it's going to be plus D. All right. So we're done with what could emerge as a D. Now, dealing with sort of the constants. Okay, let's see now. This we're done with. And then now there's going to be a minus 2 with the Y. And it's the only one. And then now these are on the operator, are operating on Y. This operator is operating on Y. And then now we have the D here on this. Right, so this is exactly 16. And then now this is also exactly minus the 16. So it's going to actually come down to 0. And then what else have we got? Right, so there is a minus 4. And then now you have this one here, minus 2. Okay, so this is going to become a 0 because D on minus 4 is going to be 0. And then it's going to be minus 8. All right, and then the minus 8 is going to go to the other side and it's going to become oh, sorry. This and this is going to be plus 8. So that it becomes minus 6. And then we have minus 4e to the twice t. Okay, we write this guy here, the green one. I can write it in green again. So we have this one. We write it in this form. We write it in the form x minus into d plus 1. Right, and then it is operating on y, and then we have 8e to the 2t minus 4. Okay, we've learned the triangular system, and it's just about learning the methods and obviously being able to use them in the event that a different question, you can always expect a different question to be provided. This kind of a module is always a walk in the park. It's one of those modules where you can get a straight A if somebody uses that terminology of straight A's. So this one is a triangular system. Or not just is a triangular system, but is the triangular system that the examiner gave to us in the beginning. Okay, so is the triangular system. Is the triangular system as anticipated? Okay, is the triangular system as anticipated or as required? Is required. All right, so we are in celebration mode because we have got it. We have got it. We have achieved the result here. But now we are not quite done as yet. Because the question was, we got the triangular systems, but we're not done. Okay, because it said show that the system this is equivalent to both the triangular systems. We have shown that. Okay, given the 3 systems above separately, state with complete justification your strategy in solving them completely. We have actually done that. Right, now there is a small remark that it's necessary to give. Okay, and the small remark that is necessary to give also in the exams as well is as follows. Right. Okay, now the system we have got, I want to comment on the nature of this system. Okay, I want to speak about degenerate systems and would say not or non-degenerate, not degenerate. Okay, not degenerate systems. Okay, not degenerate systems. Okay, so let's just continue and look at these carefully, carefully, carefully. All right, all right, all right, all right. So let's continue. All right, so we have this.
Hello.
Yes, yes, man.
What is a degenerate and not degenerate system?
Yeah, that's a good question. So there are systems that actually have unique solutions, and there are those that do not have unique solutions. So a system that tends to have a unique solution, obviously it's said to be, for example, um, is not degenerate because it has a unique solution. Okay, so I'm obviously I'm going to comment on this. For instance, from 1 and 2 above, from equations 1 and 2 above, we can be able to, we must comment on this when we have um, systems of equations. Okay, I'm just going to cite the systems here, which is exactly d minus 2 operating on x plus twice d into 1, which is 2 minus 4e to the twice t, twice d minus 3, x plus 3d. You have the operator on y, which is 0. Okay, let's look at this particular system here and comment on the nature of this particular system here. Okay, right. We will say, okay, from 1 and 2, we have there's something we call the delta. And delta now is formed by, okay, we use this all the time. And it's sort of d than just delta. Obviously, we use the delta Greek symbol so that we have the d minus 2, and then we have the twice d minus 3, and then we have twice d, and then we have 3d minus 1. Okay, we've just taken the coefficients here of this. We've just taken the coefficients here of that exactly. All right, so I want us to analyze this very carefully because it is very, very significant for us to understand this. Let us find the determinant of this. This obviously refers to the determinant of this is sort of the determinant of the coefficient matrix, okay, when you have the 2d, the d minus 2, etc. And then now this is how we study degenerate and systems that are not degenerate. Okay, let's find the determinant is d minus 2, 3d minus 1, minus twice d minus 3 into twice d. Okay, we use this even when we put into practice methods like Cramer's rule. Okay, we're going to use Cramer's rule very often when dealing with these kinds of problems. Okay, because Cramer's rule, we might need to solve for x only, or we might need to solve for y only, but we need to solve for both x and y in problems like this, generally. Right, if we therefore have this here, what is all this? So this one here, the d and the 3d is going to be 3d squared. So this is going to be 3d squared minus d minus 6d plus 2 minus 4d squared plus 3 plus 6d. Yeah, plus 6d, which is equal to, so now at this point, when you have this, you have the 3d squared minus 4d squared, which is actually, okay, so we can start with the 2, doesn't really matter. Right, we can start with the 2, and then now we come to the d terms, so it's only just going to be minus d because the minus 6d and the 6d go away. And then now we have the 3d squared minus 4d squared, which is minus d squared. But clearly this is not equivalent to the 0 operator, because this is a linear combination of operators and therefore is not equal to the 0 operator. And the conclusion so that we infer that the system, oops, okay, I'm going to be right back. Right, we infer that the system, obviously the system of differential equations we given at the beginning, the system is not, I'm going to make these capitals, it's not degenerate. And hence has a unique solution. So in other words, systems that are not degenerate have a unique solution. Otherwise, the system is actually degenerate if it does not have a unique solution. Okay, this is like a system of linear equations actually that we learn in linear algebra 1 and just linear algebra in general. So right, but we're not done quite yet, because for each triangular system, we can be in a position to show as well, because the triangular system is equivalent to the original system. So each triangular system, therefore, being equivalent to the former system, we have just performed elementary sort of raw operations by means of elimination. We call them elementary raw operations. In terms in the event of in case of matrices. Okay, now I'll just mention this in conclusion. Right, to say finally, let us consider the what? The triangular systems above. Okay, and obviously we have a triangular system in where the d operator acts on x and where the d operator acts on y. All right, so let me write this one first. D squared plus d minus 2. This operator acts on y, which is minus 6 minus 4 e to the twice t, which is x minus d plus 1 y, which is minus 4 plus 8 e to the twice t. Okay, let me just write this one. And on the other side, I'm going to write the other one we got. Okay, the other one where the d operator operates on x. So this is when it operates on on y, okay, and then there's this other one where it operates on x, so it is d squared. So yeah, I just want to discuss the degeneracy in view of the triangular systems being obviously mathematically equivalent to the former system. It's just that the system has been transformed to a triangular system. So, so you have minus 2y, which is 12e to the twice t minus 6. So now we can write the delta. Right, so we remember how we wrote the delta. So now we shall have the x and also the y. The x here, or the d operator operating on x here, is actually obviously 0, but it is a 1 there. On y, it is the d squared plus d minus 2, and the bottom one is minus into d plus 1. Okay, and then now we're going to compute this one simultaneously. Let me write the other delta for the other triangular system operating on x. Right, in which case we have that the operator on x is the d squared plus d minus 2. Operating on x is also just the d here. Operating on y is 0. Operating on y is this. So at this point, this with that is 0. So that you have 0 minus into the d squared plus d minus 2. Okay, and this is the delta, which is minus d squared minus d plus 2. So in the end, therefore, this is not equal to 0. So you have this here, which is um, so you have d here. Right, okay. Sort of cross multiplication here is minus 2, if you like. We're using what we call cofactor expansion. It's not just cross multiplication, it's cofactor expansion. Obviously, strictly speaking, you have the d here with operating on the 0. And then this is minus twice d squared minus twice d plus 4 and 0. But this is not 0. It's not equal to the 0 operator. And this is not equal to the 0 operator. What is the meaning of these? It means what we got in the beginning is what we are getting now. But now, if you look very carefully here, it is these two. If you, doesn't matter what you do, because it's minus d squared minus d plus 2. We can leave it like this and say it is not equal to 0. Okay, I'm going to say it is actually not equal to 0 here. But simultaneously, dividing through by 2 here is going to be minus that, minus d plus 2 is not equal to 0. Okay, this is just very powerful because it shows the accuracy of the mathematics and its consistency. But now we have that, this one operating on y, this operating on x, but we're getting now the delta that is equal in both instances. And now we can even compare it with this because it's minus d squared minus d plus 2. So it doesn't matter where you calculate the delta from, but we're getting the same expression from the original system to the triangular systems, and they both enhance both. Henceforth, we infer that um, the system is not degenerate. and hence has a unique solution. Okay, if the delta was 0, then the system was going to be degenerate, and if it's degenerate, then it means you do not have a unique solution. In view of the uniqueness of the solution and Kramer's rule that we often use to solve this. Okay, we're going to discuss that. Right. Okay, we're going to discuss that. Yeah. Okay, next question. Okay, I've made another question available for us to practice a little bit more. Obviously, in the next question, we are going to solve this in detail because in the first question, we did not solve. We just expressed in triangular forms, in two equivalent triangular forms. Right, but at this point now, we're going to solve by using the elimination method, the operator method. Let's just indulge and enjoy ourselves with solving this particular equation. And at this point, we're going to solve these in detail and see how to solve. And we're going to discuss the notion of what we call root vectors as well, and many other equivalent notions. Right. So what is easier to do at this point? We realize that we can just remove the easiest one because this one operating on x1 is d squared and this one is d. Operating on x2 is just d. So we can see clearly that we can just eliminate d operating on x2 easily. Right, so yeah, it is just otherwise entirely up to us. So we can just be left with d operating on x1 and now be in a position to solve that one. So let's get started. Just a mind map. Right, so with that said, what do we do? Okay, we are here. And we're going to call this one equation 1. And we're going to call this one equation 2. And then we're going to say we want to eliminate x2. Eliminating x2. Right, eliminating x2 is what we say. Right, so obviously at this point, we have the 2d here. We just need to multiply this particular one by 2. Right, and if you just multiply this particular one by 2, we have what is required. And then after that, we subtract the two equations. Right, so we're going to say 2 times equation 2. Okay, you can write the first one first, doesn't matter. And then now if we do that, it's going to be exactly 4d here minus 2 x1 4 minus twice d. You multiply by 2, it becomes 10. Okay, this is what we are able to get at this point. And after we go to these at this point, what can we actually be in a position to achieve? Right, if we wish to eliminate x2 altogether, we can then multiply. Okay, let me change the strategy and do it this way so that we are very effective. It doesn't matter, but yeah, I want to put more operators at once so that we are very effective in our strategy. It doesn't really matter. But if we say eliminating x2 is a strategy, So we're gonna take the first equation and multiply it by twice d, like twice minus d. And then now we're gonna multiply the first equation by, we want to eliminate x2, so we can just multiply it by 2 minus d. And then obviously then we'd have to multiply this one by twice d. So twice d times equation 2. Okay, if you multiply this one by this here, so it's going to be exactly 2 minus d. Yes, d squared plus 1. And then now we multiply this one as well by 2 minus d. And then it is x2. And then we multiply here. It becomes 2 minus d twice t. Okay, this is effective. Let's just try to be just get rid of x2 altogether. You can see the approach being slightly different from that of the triangular system because we are trying to save time here, but we could do it like we did before. But yeah, we're trying to save time, make sure that x2 is out. But in the former triangular systems, we could have both in the same equation, like x and y. Right, so here now we multiply straight up actually by twice d. So it's going to be twice d minus 1. X1 minus, you multiply this one by twice d, which is x2. And then you multiply by twice d. Okay. So what do we get here? Okay, this is what we achieve. Now, these ones, we can give them big names. We can give them names and say, okay, we can call this one 3 and call this one 4. Okay. If you look at now these two things, they're actually very much the same, except that, well, they even have the same sign. So x2 is out. So a more powerful bulldozer method than the former triangular system method we used. Now, at this point, we can just subtract the two equations in order. So we're going to say the first one minus the second one. We're going to say 3 minus 4. Once again, you can say 4 minus 3, depending on, but yeah, the same thing. So, but now we can see that clearly x2 is out, and we're making significant progress. And then we're left with this. Okay, if we're left with the x1, okay, let me just minus 2 minus d, and then we have d squared plus 1, and we have x1, and we have minus this. Right, and so we have that. Okay, this minus that becomes 0, and then we have the top one, and then we have twice t minus twice d on 5. Okay, this is already 0, this the d on 5. So let's just do some basic arithmetic here. 2 times d squared. You can write twice d squared. 2 times 1, it's actually 2 minus d, and that is minus d cubed. Minus d and 1 is actually minus d x1. And then we can multiply also here in terms of this. So if we multiply these, what do we get? Okay, I'm gonna Just remove the x1 because there's x1 everywhere. So I can just have a single x1 and just have the like terms edit within. So you're going to have this here, and then you're going to have minus 2d in that, which is minus 4d squared. Which is minus 4d squared plus twice d, and then you have that. So analyzing this, so you have 2 times 2t, which is 4t, minus the, the derivative of the t of 2t is just 2. So you can just write minus 2 there. And then here, this one is 0 because 5 is a constant. The derivative of the constant 5 is 0. Okay, now let's just come to this one and write it properly. So it is minus d cubed, right? And then we have this and this, which is minus twice d squared, which is this and that. D cubed and minus twice d squared. Okay, there is twice d minus d, which is d. Which is 4t minus 2. Okay. Okay, we have made progress in just one sort of systematic major transformation of this. We should have used the triangular, but yeah, this is just super, super powerful. Okay, this is how we do it if we have the system to solve. Okay, now let's write this one on the next page, which is minus d cubed minus 2d squared plus d plus 2 operating on x1 4t minus 2. Right, taken from the other side is actually minus d cubed. We're just learning how to solve this. Okay, minus 2d squared plus d plus 2 is actually operating on x1, which is equal to 4t minus 2. Okay, so this one is solved in 2 stages. It's just a differential equation now. And so it's solved, it's a third order differential equation, right? Written in terms of the d operator, right? So we need to solve this one in using our two measure methods. We need to first find the auxiliary equation. So the auxiliary, right? The auxiliary equation is, what is the auxiliary equation? Is the equation that's written in terms of, normally we use m straight away. For the auxiliary, so this becomes like an m cubed. So you can write minus m cubed here, and this one becomes minus 2m squared. So the d becomes like an m, and then here it becomes plus m plus 2, and then this here is always, we form a homogeneous equation. So yeah, so this auxiliary equation is of the homogeneous. We completely forget about these. We're going to consider these later on. So we equate these to 0, and we have that. At this point, we have m cubed plus twice m squared minus m minus 2 equals 0. So which is m? Minus into m plus 2. M plus 2 into m squared minus 1. M plus 2 into m minus 1 into m plus 1. m m m minus 1. Those are your roots. Okay, the auxiliary equation is this one. Then you have the complementary function. Write the complementary function. What is the complementary function? The complementary function is obviously it's a function of x1, a function of t. It is x1 a function of t. And then we call it the complementary function, subscript CF. And this is actually the same as the following. Okay. So we just continue, please. I'm just continuing now. So we have this one here. Okay, just 1 minute. Right, setting up my system just once more. Right, so we have the complementary function, which is actually this one here. And now because these are distinct roots, so we have, okay, in which case they can be distinct or they can be like, okay, they can be the same. Okay, you can have like equal roots. So, but you can have distinct roots, in which case, in this case, we have distinct roots, so it's much easier. It's common. And that's what so possibly we learn first. We learn this one. And then we continue. We continue. Okay, the complementary function as it is given, it is C1 e to the minus 2t plus C2 e to the minus 2t, then we have minus t, constant 3 e to the t, like 1t, 1 times t, which is that. Obviously, we do this and we mention that where C1, C2, and C3, what we call them, they are arbitrary constants. Right, so with these ones, C3 are arbitrary constants. Okay. So we have found the complementary function. And then after we've found this complementary function, we need to find the particular solution. So, yeah. Let's find the particular integral. Right, so the particular integral is given by right. So you have minus d cubed minus twice d squared plus d plus 2 x1 which is 4t minus 2. And then now we have seen that we can multiply through by -1. So that implies that we can have d cubed plus twice d squared minus d minus 2 with the operator x on x1, and then this becomes 2 minus 4t, like that. Okay, so you can write it exactly in that manner. Exactly in that manner there. Right. Okay, obviously this is a very, very subjective step. So you can write either like this, or you can write, you can still continue with the minus. Now, you need to factorize these. Let's factorize these. Well, you might just write, doesn't matter what you do. You can take the inverse operator. Now, taking the inverse operator means, therefore, you have x1 particular integral as a function of t is actually the same as 1 divided by d cubed plus 2d squared minus d minus 2. And then you have here, you can write minus 4t plus 2, like this. At this point, this is too easy to factorize, because you can see that you can pull out d squared to getting d plus 2, factor out -1, and you have this here. And this here is the operator on minus 4t plus 2. In the denominator, you have d squared. So you have this one here. So we have this. Difference of two squares for the d squared minus 1. So you have d minus 1 into d plus 1, difference of two squares, and then you have d plus 2. Okay, and you have minus 4t plus 2, like this. Okay. Now there are certain things you need to always remember: the Taylor series. Yeah, Taylor, you can call it. There's different names, but Taylor is the most general term. So we use it here as one of the most powerful results. There are two of them. The first one is the high school one, 1 over r for the geometric series. 1 over r plus 1 is 1 minus d plus d squared minus d cubed plus, yeah, we're going to have this one here. So which is 1 divided by. Okay, so we're going to use it first here on that one. So using it on that one, then we're going to factor out the d plus 2. And then you have the d minus 1. All right, so this one is going to become, the 1 over d plus 1 is going to become 1 minus d plus d squared minus d cubed. Okay, we're just discussing how to solve now a system of two differential equations using the d operator methods. And then now you can write here minus 4t plus 2, like this. Right. And then now we just let these operate on this one. Okay, next page. So which means that if we continue and have our x1 particular integral, a function of t, which is 1 over d plus 2 d minus 1 into 1 minus d plus d squared minus d cubed plus dot 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 into minus 4t plus 2 x1 particular integral All right, so let's write this one. D plus 2. Okay, we're just also practicing how to deal with the D operator. Okay, this one multiplies 1. Okay, if you now differentiate this whole thing with respect to, well, differentiating 4t plus 2, the derivative of the 2 is 0, and that is minus 4. Okay, obviously, if you differentiate first, the first derivative is minus 4. The second derivative is going to produce a 0, and so on. And this is what we achieve. So it means that x1 particular integral of t which is d minus 1, so which is 6 minus 4t. And then now we do the same. This one in view of the Taylor series. Where a Taylor series is going to be 1 divided by 1 minus d. It's always 1 first. So it becomes 1 plus d. So now because there's a minus, then every term has like a plus here in the sum, in the infinite series. So, which means that we have x1 particular integral function of t. Okay, if this one now we want it to be like this, we want it to be 1 minus d. So we can factor out a negative and do whatever we like. This negative is going to make this one 4t minus 6. Let me write like this first. All right, so it's going to make that one 1 divided by 1 minus d. 4t minus 6. Okay. So which means 1 over d plus 2. Now we have this one, using that one. It's 1 plus d squared plus d cubed. And then we have 4t minus 6. Okay. Now we let this operator operate on this linear expression. These being d plus 2. Okay, these times 1 is just 4t minus 6. Okay, the first derivative of the 4t minus 6 is just going to be 4. The second derivative of these is going to be 0, like we saw, and so on. This is 1 over d plus 2. 4. 4t minus 2. Okay. This is what we get. Now we're just left with this one, so we must just transform it to look like that one. So I'm going to just divide the board here. And you're going to have x1. x1 particular integral as a function of t. At this point, we can just pull out 2 from the denominator, giving us 1/2 into 1 out of 1 plus d out of 2, which is 4t minus 2. x1 particular integral of t. We have 1/2. So we're using that formula, but now here it has a plus, so the signs alternate. So it's going to be 1 minus d over 2 plus d over 2 squared minus d over 2 you cube it, which is 4t minus 2. So it is 1/2. Okay, multiply this by that, which is 4t minus 2. Then if you, here you have minus 1/2. The first derivative is 4t minus 2. We saw that the second derivative of this is going to be 0, so can close. Okay. So which is x1 pt. Okay, let's just deal with this. Let's deal with the inside. What is inside the parenthesis? Like there's a 4t, then there is minus 2t, which is 2t. 4t minus 2t, which is 2t. Then you have minus 2 plus 1. Minus 2 plus 1. Minus 1. So what is then the particular integral here? Okay. Let me see what we have got here. Okay, I made a mistake here. Okay, because when you find the first derivative here, it must just be 4 only. Must just be 4 only. So if minus half, the first derivative is just going to be 4, but I wrote many things. Yeah, then you close. So it's going to have an effect on. Okay, let me see here. So yeah, you have this. So you have 4t minus 2t minus, rather minus 2, which is minus 4. Like so. And therefore the result is that x1 is the particular integral of t is twice t minus 2. Okay, so we got the particular integral, but we also got the complementary function, and hence we have the general solution. Hence, the general solution is given by the general solution. I want to say first, the general solution for x1. Let's say that because we have two variables like x1, x2. So the general solution for x1 is given by x1t. Okay. Which is x1 is a function of t, which is x1, which is the complementary function of t plus x1, the particular integral of t which is x1 of t. Okay, so we remember that this one is c1 e to the minus twice t, c2 e to the minus t plus c3 according to the roots of the complementary of the auxiliary equation. e to the t, then you have, okay, this is actually the complementary function. And we have seen that the particular integral is twice t minus 2. Now we find, now we find x2 a function of t because we've already got x1. But we note that we're done, obviously. Please, from 1, we have, okay, so we have the equation 1. What is the equation 1? We remind ourselves. Okay, this is the equation 1, which is actually exactly this one here. D squared plus 1 into x1. We just solve for x2 from it. So we're going to write that one down straight away. D squared plus 1. So here we're going to have d squared plus 1 x1 minus 2d x2, which is equal to twice t. Okay, that is equation 1 as it is. But we need to now use one of the equations, and one of them, these are just like Smaltius equations. So we need to use this one, but we want to solve for x2. So to solve for x2, we make dx2 the subject of this equation. And making dx2, we have dx2, which is exactly the same as 1/2. Then they take this one to the right, etc. So it becomes 1/2 d squared plus 1 x1. Then there is this one goes to the other side, and this is minus that. So you have this here. Okay. Now we do substitution into that, and we find the derivative, etc. Okay, so call this one equation something A, and call this one equation B, and then proceed to say substitute A into B. So we have this. Right. Remember there is x1, you put this long thing. C1 e to the minus that. C2 e to the that. C3 e to the t. 2t minus that. Okay. Right. We have this one now, and then we have minus 2t. So dx2. We want to solve for x2 out of this. So what do we achieve here? So we will first allow the d squared to proceed and differentiate everything here. So, but to differentiate twice. First, it's going to be -2, and then it's going to be 4. So it's going to be 4c1e to the -2t. Differentiate twice, it's going to be -1, 1. So it's going to be c2e to the -t. And then next here, this one is just derivative of e twice, doesn't change. E to the t. And then now, obviously, we proceed. We look at this other one here. So this is only e. Then this one here is going to be 0, 0. Okay, because we're doing twice. Right, first time is going to be 2, and then the next time is going to be 0. So this is going to be 0. So d squared has already done its job. We just now to just multiply everything by 1. We're keeping the half outside. So it's just going to become c1e to the -2t, c2e to the -t, c3e to the t, 2t minus 2. So we kept the half outside, and the -2t was just sitting over there. And then now we proceed to, okay, this is a 4. Now, in view of this thing here, any like terms here, there's a C1, C2, C3, and there's another C1, C2, C3. And then we have this one is actually the twice 2. So, which is twice t. So it's going to be twice t, which is dx2. Okay, if you have the 4, c1 is going to be 5. c1 e to the -2t. Then you have the c2. There are 2 of them. Okay, just check that there's no mistake there. There are 5 of them. Okay, it appears that there's a C2 there and there's a C2 there. There are 2 of them. Let's just write that one down. Yes, 2C2 e to the -t. Then the C3s, there are also 2 of them. C3e to the t. Okay, we're done with the C3 now, and then you have the twice t minus 2 minus 2t. Okay, I need to clarify that we divided through by 2 here, so this one's supposed to be 1. Supposed to be 1. So we divided through by 2, but yeah, this is supposed to be just minus t here. Okay, we even forget. So T here, T there. Also, this one, T here, T here. T here, T there. So, yeah. So, which means that at that point we have dx2. We allow the half to distribute everything through the brackets, giving us 5 over 2 c1 e to the minus 2t plus c2 e to the minus t plus c3 e to the t plus t minus 1 minus t, giving us dx2 is 5 out of 2 c1 e to the minus 2t plus c2 e to the minus t plus c3 e to the t minus 1. The t minus t boils down to 0. Okay, we're done. Now we are just learning also the d operator method and how it works. But obviously at this point, now we just need to make x2 the subject. So to make x2 the subject, we sort of multiply by the inverse operator, which means that we shall have x2 as a function of t, 1 over d, which is 5 out of 2, c1 e to the minus 2t, c2 e to the minus t, c3 e to the t minus 1. So we sort of multiply by the inverse operator, or we take the inverse operator. We take the inverse operator as sort of the right mathematical terminology, because it's an operator, it's like a function. So we take the inverse operator both sides, like if you could take the inverse tan function, inverse sine, inverse cosine. Okay, once we have these, then we integrate this. 1 over d means we are integrating. So if you integrate now, we integrate this one with respect to t. So this one is going to produce minus 1/2. So it's going to actually become minus 1/4 c1 e to the minus 2t. And then now this one is just going to produce a minus. So a minus c2 e to the minus t. This one is going to produce a c3 e to the t. This one is going to produce a minus t. So that is x2 that we got. So we got x2 to be this, but we need to remember x1. X1 is this. So what do we have here? We have that x1 is this guy here. Okay, this one. X2 is this one here. So we have x1 and x2. And therefore we are done. Because these are the answers as required. Because the question was solve the system using or by using the elimination method, the operator method. And we use the elimination We first solved for x1 and then next we solved for x2. And we found the auxiliary equation, the complementary function, and we found a particular integral, etc. Okay, we're going to learn more about this. Right, so we are going on to solve more problems. The next thing we shall discuss is this particular type of method where we need to be in a position to solve these particular type of problems. Right, so for instance, now solve the system. Why is there a unique solution to the above system? Right, first and foremost, this one is actually an ordinary differential equation, which is a matrix equation. So we're gonna deal with this one. So to solve this one now, what we do is we take this matrix here and we say 0 minus lambda, 1, 0, 0, 0 minus lambda, 1, 2, 1, minus 2 minus lambda. Okay, so we have this. Okay. Ideally, we take the determinant of this normally, of this matrix, but obviously first we find the matrix and then we take the determinant. Okay, so we can just simplify. Okay. My goodness me, this one. 2, 1 minus 2 minus lambda. Okay, using cofactor expansion, we associate a couple of signs with this, like associate a plus here, a minus, then a plus. So we're going to have minus lambda. Okay, if we cover this row in that column, we're left with minus lambda 1, 1 minus 2 minus lambda. And then you have minus 1, which is 0, 2, 1 minus 2 minus lambda, which is minus that. Multiply this with that, which is exactly lambda squared plus 2 lambda minus 1. This is minus 2. So you multiply out. So which is minus lambda cubed minus 2 lambda squared plus lambda plus 2. Here you can factor out lambda's negative lambda squared. Factorize this, so it becomes lambda plus 2. And then we have lambda plus 2. And then this is actually lambda plus 2 into, you can write it as 1 minus lambda squared or minus lambda squared plus 1. Right, so at this point, we obviously need to equate this to 0. And then we have lambda equals -2. Lambda squared equals 1, which means lambda is plus or minus 1. So for lambda equals -1, we need to get the eigenvectors. So these are the, what you call the eigenvalues. Okay, let's get the eigenvectors. So for lambda equals this one, the eigenvectors now. So we shall have this one here. It's going to just become 1, 1, 0, 0, 1, 1, 2, 1, -1. And then you do V1, V2. Okay. Now let's write this one on the other side. It is exactly this one, so you note it. It is 1, 1, 0, 0, 1, 1, 2, 1, -1. So it is exactly 1, 1, 0. Okay, it looks like an 11, that one. So it's 1, 1, 0. 1, 1, 0, 0, 1, 1, 2, 1, -1. Which is V1, V2, V3. Zero, zero, zero. 1, 1, 0. 0, 1, 1, 2, 1, -1. 0, 0, 0. Where you write the augmented matrix because you want to get the eigenvector. So I might not finish this question because it's a bit long. I might finish it tomorrow. So you obviously here you have 1, 1, 0, 0, row 2 -2, row 1. So it becomes -2 times that. You add is 0, -2 times that is -2, you add is -1, -2 times that you add is -1, -2 times that you add is 0. Right. So if you have this, row 1 minus row 2. So you have this. Row 3 plus row 2. So, okay, we have this. So this one is V1. V1 minus V3 is 0. V2 plus V3 is 0. And this means V1 equals V3. This means V2 equals minus V3. The eigenvector associated with this is the v1, v2, v3 vector. So v1 is v3, v2 is minus v3, v3 is v3. v1, v2, v3. Right, so okay, v3. So it's 1 minus 1, 1. And then the eigenvector for lambda equals minus 1, the eigenvector is 1 minus 1, 1. Hence, x1 of t is c1 1 minus 1, which is e to the minus t. It's sort of a solution. It's one of the solutions x1t associated with lambda equals minus 1. Okay, let's just put in a little bit of energy and try to finish this off quickly. Okay, for lambda, a couple of values of lambda, like there's also lambda equals minus 2, because we got the values of lambda from here. Minus 2 is there. So associated with that one, we're gonna have the following. Okay, there's that matrix that we got. So I'm not really gonna waste a lot of time. It's gonna be 2, 1, 0. There's a lambda matrix 2, 0, 2, 1, and then 2, 1, 0. So this is W1, W2, W3. And then it's 0, 0, 0. Right, to save a lot of time, I know that we know how to row reduce, or would say therefore that this one, like we saw the row reduction, reduce row echelon form would be W1, W2, W3 is the same as 1 minus 2, 4. And this gives us a solution. Okay, so for, I'm going to write the solution. For lambda equals 1, there's also this matrix here. So for lambda equals 1, the matrix is, from that lambda matrix is minus 1, 1, 0. 0 minus 1, 1. 2, 1 minus 3. Okay, in any order, I would call this one U1, U2, U3. It doesn't really matter. And this is 0, 0, 0. This is U1, U2, U3. So at the end of the day, which is 1, 1, 1. Okay, and therefore this means that, yeah, can we use a different color? So it means that if I use red, just to make sure it's very different, you would have therefore the solution. So I'm gonna call this one x2 of t. And x2 of t is gonna become C2 1 1 1 e to the t. X3 of t. C3. Okay, so it's this one, the vector. So it's 1 minus 2, 4 e to the minus 2t. Right. Okay, now we then say hence. Hence the solutions. And the solutions are, now we're going to have x of t, which is equal to x1 of t plus x2 of t plus x3 of t. And what is this? Right, so this here is exactly C1, 1 minus 1, 1, e to the minus t plus C2, 1, 1, 1, e to the t plus C3 into 1 minus 2, 4 times e to the minus 2t. Obviously, this is true where C1, C2, C3 are arbitrary constants. Okay, obviously we're trying to familiarize ourselves with the actual methods here. Or arbitrary, I can see the time. That's why I'm rounding off. Arbitrary constants, just need to sum it up. Right, where the C1, C2, and C3 become arbitrary constants. Okay, so in view of the initial condition, right, in view of the initial condition, which is this one, x0, which is 1, 0, 1, which is 1, 0, 1, and if x0 is 1, 0, 1, it would therefore mean that at this point, what we have is that t0, so we have 1 minus 1, 1, plus c2, 1, 1, 1, plus c3, 1 minus 2, 4, so which means that you have c1, right? So what we have is therefore c1 plus c2 plus c3. C1 plus C2 plus C3 is 1. Minus C1, plus C2 minus 2C3 is 0. C1, C2, C4, C3. C1, C2 plus 4C3 is equal to 1. Okay, obviously here we're just okay. This one is easy because the roots are all different. We shall just talk about root vectors as well in cases when the actual roots are different. So obviously this implies that C1 is 1/2 and C2 becomes the same value or has the same value and C3 becomes 0. Okay, you can to solve this, it's all matrices. So you can just solve this using what we call the Gauss-Jordan elimination method. And as we use the, after we use the Gauss-Jordan elimination method, I'm going to write the final answer to this. So now the final solution is as follows. So hence, which is xt. Okay, so you come here now, like so. You substitute everything there. You substitute here the C1, which is half, and C2, which is also 1/2. And then C3 is going to become 0. So you're going to have 1/2 into 1 minus 1, 1. E to the minus t, C2 is 1/2, 1, 1, 1. E to the t, like this. And then C3 is going to become 0. Right. Right. So obviously at this point, this is the solution. Is okay, because I want to also mention that in view of theorem, we're going to discuss these theorems in detail tomorrow. In view of theorem 2.29, we have three different eigenvalues. Okay, we have three different eigenvalues. Right, because we have three different eigenvalues, we have three different eigenvalues. Then x dot which is ax, the original differential equation in matrix form, with the initial value, this one here, initial value which is x sub 0. This system has a unique solution. That system has a unique solution. And now we have found the unique solution, and this is the unique solution. Okay, this is the unique solution, and we're done. I think, yeah, I must thank you for joining us today. And I can see the time has elapsed a little bit. I was just trying to race to get this one concluded. There are more things I'm going to discuss tomorrow, everything that pertains to exam. There are also other very obscure notions we're going to discuss tomorrow as well, because yeah, there are several things I'm going to discuss tomorrow, so I'm going to reveal them tomorrow from the material. But exam-oriented stuff, yeah. So I'm going to post a video in the next couple of minutes. Yeah, but yeah, we'll talk a lot more tomorrow. So what is very important is just making sure that this is just clear, and if repeated these questions, you can be able to tackle them. Okay. So yeah, thanks for joining us today. Is my plan to see you tomorrow at what time? At is my plan to see you tomorrow at 4:30? So you let me know if 4:30 is ideal, so that we look at some other things that are obscure. And other solutions to other differential equations using different methods, the um, root vectors and other things in the event of even repeated roots here. Okay, so we shall see that. All right, yeah. So thanks a lot. I'll see you tomorrow at 4:30. Okay. Thanks a lot, and goodbye.